All right, welcome back to the AI Research Roundup. I am your host, Alex. Today, we're looking at a fascinating paper that's been trending, titled SEW, Self-Evolving Agentic Workflows for Automated Code Generation. The core problem it tackles is that while we can use multiple AI agents to solve complex coding tasks, the process for how they cooperate is usually designed by hand. These preset plans are called agentic workflows, and they're often rigid and don't adapt well to new problems. This paper introduces a framework called self-evolving workflow, or SEW. It automatically designs and optimizes these agentic workflows, essentially letting the AI system figure out the best way for its agents to work together. This automated approach showed a huge 33% performance boost on a challenging benchmark. And for those of you who want to dive deeper and try this out, the authors have released the code for this work on GitHub. The repository is called Evo Agent X, and it's an automated framework for evaluating and evolving these agentic workflows. It comes with installation guides, code examples, and tutorials to help you get started. So to see this in action, the paper gives us a great visual. On the left, we see the initial setup for a simple coding task, calculating the sum of squares. It's a basic workflow with just a code generation agent and a code rewriting agent. And, well, it produces the wrong code. But on the right, we see the system after the self-evolving workflow framework has done its work. The workflow is more sophisticated. Now it includes a task rewriting agent and a code reviewing agent. And this new, evolved system successfully generates the correct code. This really illustrates the core idea, evolving the entire process, not just the code. Okay, so that example showed the before and after. And this diagram really breaks down the how. The self-evolving workflow framework operates in three main stages. First is workflow generation, where it creates an initial team of agents from a template. Then comes workflow evolution, which is where it actually changes the team structure, adding or rewiring agents to improve the overall process. Finally, you have agent evolution, where the individual agents themselves get smarter. The paper explores two key strategies for this. One is direct evolution, or DE, where the system directly rewrites an agent's instructions. The other is hyperevolution, or HE, which first improves the rules for how to make changes, and then uses those new rules to upgrade the agent. It's a really clever, multi-layered approach to improvement. So building on those two strategies I mentioned, direct and hyperevolution, this diagram gives us a closer look at how they actually work. Okay, with direct evolution, you see a mutation prompt, which is essentially an instruction on how to change the agent's main goal, is used to make that agent's prompt more creative. Second-order evolution then takes that new creative prompt and refines it even further with another mutation instruction. Now, hyperevolution is where it gets really clever. Instead of just changing the agent's prompt, it first improves the mutation prompt itself, using what the paper calls a thinking style prompt to guide the change. It's like improving your editing tools before you start writing the document. This really shows the different layers of optimization at play. Alright, so for the system to actually evolve these complex workflows, it first needs a way to write them down in a language it can understand and modify. This figure shows two of the different formats the researchers explored. At the top, we have what's called Business Process Model and Notation, or BPMN. It's a very formal, structured way to define a process, almost like a flowchart written in code. Then at the bottom, there's the Code Representation and Execution, or core scheme. This one is much more straightforward. It's basically a simple, step-by-step list of tasks. The paper explores which of these text formats the LLM finds easiest to read, understand, and ultimately improve upon. Alright, so after looking at how the system represents these workflows, the big question is, does all this complexity actually pay off? This table gives us the answer. We're looking at performance on 3 coding benchmarks, including the very challenging live code bench. The main metric here is pass at 1, which is the percentage of problems where the very first generated solution is correct. And the results are pretty clear. Across the board, for both the GPT-4o Mini and Gemini models, the self-evolving workflow framework, or SEW, consistently comes out on top. For instance, on that difficult live code bench dataset, SEW boosts the GPT-4o mini model success rate from 38% all the way up to 50.9%. That's a huge improvement over the base model and other advanced methods. So, given those great results, a key question is, which workflow format actually works best? This table gives us a look at that. It compares the different representation methods we talked about earlier, like business process model and notation, and code representation and execution. It uses two metrics. First, the logical successful rate, which is just how often the LLM can correctly parse the workflow's structure. And second, the generation successful rate, which measures if that workflow actually leads to working code. Interestingly, while the formal BPMN and Python formats were easiest to parse, it was the code representation and execution scheme that was most effective for actually creating usable code, with the highest generation successful rate. So, knowing that the code representation and execution scheme is a good format, this next table really isolates the two key evolutionary steps in the self-evolving workflow framework. It helps us see how much each part contributes to the final result. We're looking at two specific workflows here, a task parsing workflow and a code rewriting workflow. The table compares what happens when you only evolve the workflow structure versus when you also evolve the agents within it. And the results are very telling. Just evolving the workflow gives a solid performance boost, but when you add agent evolution on top, that's where the magic happens. On the difficult live code bench dataset, this coevolution boosts performance by an additional 20%. It shows that creating a good structure is the first step, but optimizing the agents is what truly unlocks its potential. So to wrap things up, this work on the self-evolving workflow framework really highlights a powerful idea. It's not enough to just create a smart process. You also have to optimize the individual AI agents that carry out that process. This co-evolution of structure and agent is what pushes performance to new levels, making complex code generation much more reliable. It's a fascinating look at how we can build more effective autonomous systems. Thanks for tuning in. I'm Alex, and this has been the AI Research Roundup.